We defined similar matrices to be matrices that are representing matrices of the same linear transformation. So two matrices are similar if they represent the same linear map with respect to different bases. That was the definition. And then we had a theorem, which we didn't prove, that gave an equivalent definition of similar matrices in terms, in the realm of matrices alone. Namely, there was the existence of an invertible matrix P such that B equals P inverse AP. Okay, everybody remember? Okay, so I mentioned that similar matrices share many properties, and this is what I want to discuss now. And I want to start with defining a property that we haven't discussed yet, which is the trace of a matrix. So here's the definition. The sum of the main diagonal elements of a square matrix, A n by n, is called the trace of A, and denoted by TR of A. So right now we're just going to encounter this definition and not say much about why it's important and where it's used. Okay, so for now it's just a reasonable thing to define. Motivation is yet lacking. So the trace is just the sum of the diagonal elements. So here's an example. Suppose you want the matrix pi 3 root 2. I'm just throwing in some interesting numbers that I know. -1, e, 1/2. And in fact, I have no clue why I'm copying this off my page. I can just invent it and put anything. So what is the trace of this matrix? Right. All you have to do, very easy thing to calculate. The trace of this matrix is just the sum of the diagonal elements. So it's just pi plus e. Good? Okay, so that's the notion of a trace. And here's a little theorem regarding traces. If you take two matrices, square matrices, and the trace of the product equals the trace of the product the other way. Okay? So these are square matrices, so they can be multiplied both ways. This is not a claim, of course, that AB equals BA. If it were, then this would be an obvious statement. It's not, because matrix multiplication is not commutative in general. Okay? So let's prove this. Proof. So what I want to do is decipher what are the diagonal elements of each of these products and what is their sum. Okay? So the diagonal elements, in general, let's start with the general statement. What's the ijth element of the product AB? The ijth element of the product AB, I'm going to use sigma notation, hoping that you're already not too terrified when you see it, is the sum over, let's say k goes from 1 to n, let's say these are matrices of size n by n, of A, I, k, b, k, j. Remember? Okay, so this is the formalism of what we know. Look up here a second, going like this times like this, right? The ith row of A times the jth column of B. So that's the formal way to write it. So that's the ijth element of AB. And therefore, what is the diagonal element? A diagonal element would be an element where you have II, right? That's a diagonal element, same row and column. So it's a sum, k goes from 1 to n, aik bki. Good? Okay, so that's the ith element. So now let's calculate what is the trace of AB. The trace of AB is the sum of these guys. So we have to sum over I goes from 1 to n, of all these guys. So there's another sum of sigma k goes from 1 to n, aik bki. Good? Okay, what is the trace of BA? Let's do it slowly and carefully. I agree that it is, once you can see through the notation, it's rather trivial, but the notation is sometimes a barrier. So let's do it carefully. So the trace of BA is again the sum. Let's write an intermediate step. The sum over I equals 1 to n, of these elements, but for BA, of BA II. Do you agree? Okay. And what is BA II? So I'm carrying this sum over. Sum I over I goes from 1 to n. And BA II would be the same thing here, but interchanging the B's and the A's, right? So it would be again a sum. K goes from 1 to n. But now the first matrix is B, so it's BIK AKI. Do you agree? So in both cases, we have a double sum of products. And here I can, of course, reverse the order of the B's and the A's. These are products of numbers, of entries, and that is commutative. So I'm summing over two summation indices, I and k, both range from 1 to n. Here I have the AIKs, meaning BKIs. Here I have AKIs, meaning BIKs, but that's the same thing. Okay? Do you agree that this is precisely the same number? This sum and this sum are precisely the same. Okay? Now, if you have a hard time viewing it, what you have to do is open the sigmas and convince yourself that what you're seeing is precisely the same elements. Okay? So these two, let's write it like this. These are equal. Good? Okay. So, and by the way, if you're scared because of this completely, here's the best way to at least feel comfortable with it. Take a couple of 2x2 matrices, concrete ones with numbers, multiply them one way, multiply them the other way. You won't get the same thing in general, but you can see that the traces are the same. Take a couple of 3x3 matrices and do the same thing. Okay? Everybody good? Okay. So here's the theorem. So this was the notion of the trace and an important property of the trace. And here's the theorem that takes us back to similar matrices. And it says the following. Suppose we have two similar matrices. A is similar to B. That was our notation for similar matrices. Okay? Then,
can I have a little question about
sure.
sigmas?
Yep.
It's like this because you can switch the sigmas, yes?
When you're, so we're back here a second. When we do finite sigmas, okay, in calculus you do infinite sigmas, but we're not there. These are finite sums. For finite sums, you have associativity of numbers. Associativity, commutativity, distributivity, all these properties we know from the field R or C. Okay? So you can switch the order of the sigmas. You can rename I, you can call I J, and then change all the I's to J's. Okay? You can call I K, That would be a bit tricky because you already have a k here. So do a temporary switch. Call I j. It would be the same. Then call k I. Would still be the same. And then call j that you have here k. That's something you can do. You're just changing names. And you'll see that you get the same thing. That's another way of seeing it. Okay? Okay. Back to our theorem. Then, three things hold. One, the determinant of A equals the determinant of B. Two, the trace of A equals the trace of B. And three, the rank of A equals the rank of B. So these are the three properties of matrices that we already know that are shared by similar matrices. Okay? What I want to do is prove 1 and 2. I'm not going to prove 3. It requires some additional, let's say, lemmas, some properties that we haven't discussed and that would take us a bit off track, and I don't want to do it right now. Okay? But it is still a valid theorem. So I want to prove 1 and 2. So let's start with proving the one about the trace, because that's the one we just discussed. So proof of 2. So I want to show that the trace of A and the trace of B are the same. And I'm going to resort to the definition of similarity via an invertible matrix P. Okay? So the trace of A, or let's do it the way we wrote it. We wrote that B equal. It of course doesn't matter, but let's stick to previous notation. So the trace of B is the same as B itself. Since it's similar to A, there exists some invertible matrix P such that B is P inverse A P. Okay? Here I use the fact that B and A are similar. Therefore this equals, therefore the traces are the same. Okay. Here I have a product. I have P inverse A times P. Okay. I'm thinking of this as a product of P inverse A times P. I can rearrange the order. That's the previous theorem that we had. So I can write this as the trace of P times P inverse A. Do you agree? By the previous theorem. P inverse A times P and P times P inverse A, these are not the same matrices, but their traces are. Good? And what's this? P times P inverse is I times A. So this is just the trace of A. Good? So very straightforward. Similar matrices have the same trace. Using, of course, the fact that this is an equivalent definition of being similar. Okay? Okay. Let's move on to showing that determinants are the same, and it's going to be very similar. Very similar. Maybe let's rewrite this and have it all fit on the same board. Proof. So this is the proof of 2. And here's the proof of 1. So what's the determinant of B? The determinant of B, again, using the fact that they're similar, is the determinant of P inverse A P. Right? That's using the fact that B and A are similar. Now, a determinant of a product is the product of the determinants. That's something we know. So this is the same as the determinant of P inverse times the determinant of A times the determinant of P. Do you agree? These are properties of the determinant. Another property of the determinant is we know what the determinant of the inverse matrix is. The determinant of P inverse is 1 over the determinant of P. Remember that? So this is the same as 1 over the determinant of P times the determinant of A times the determinant of P. Good? Now, these are numbers. The determinant of a matrix is a number. I can calculate them in any order. They're just numbers. And of course, P and 1 over P cancel out. And by the way, how do I know that this determinant is not 0? I'm taking 1 over it. Right, it's an invertible matrix, and we know that for invertible matrices, it's if and only if the determinant is not 0. Remember? Okay, so this just equals, I can cancel P and 1 over P, and I get the determinant of A. Good? So, sure.
Because all the determinants are numbers,
right.
I can switch between them, right?
Once you have them separately,
yes,
you can switch between them.
And then I can connect them again?
Yeah, okay, so you're asking, suppose I moved A over here,
yeah,
and then said the determinant of P inverse times the determinant of P is the determinant of P inverse P, which is the determinant of I, which is 1. Very good. Wouldn't make it shorter because this was short as is, but would be an alternative proof which is just as correct. Very good, very good. Good, everybody follow the idea here? Okay, very good. Okay, so as I said, I'm not going to prove 3. The last thing I do want to do is to show this on an example, show these properties really hold on an example. And since we already had an example, I'm just going to continue that one. So I wrote a reminder here. We looked at a linear map from R3 to R3, which takes ABC to minus AB0. Remember this? We spent a while on this, right? And in particular, we found it's representing matrices with respect to the standard basis, 1, 0, 0, 0, 1, 0, and 0, 0, 1. And we found separately its representation matrix with respect to a basis we called F, which was 1, 1, 0, 1, 0, 1, and 0, 1, 1. Everybody remember this, right? Okay, and these are the two matrices we got. Let's see that they indeed share these 3 properties of the determinant, the rank, and the trace. Okay, so indeed what we have to do is calculate all 3 for each of the 2. Okay, so for this, let's call this one A, and let's call this one B. They're similar by definition. They're matrices that represent the same linear map. And we even saw the similarity matrix, the invertible P, that does the job, right? We even calculated what P and P inverse are and showed that B is P inverse AP in this example. Okay? Remember, everybody with me? Okay. So once I have a different shirt, it means that it's a different day we're recording on. I pay attention not to wear the same shirt again and again. So it's a different day, so people sitting here have seen this but a while ago. Okay, so everybody good? Okay, so let's calculate some stuff. So what is, for example, the trace of A? A is this matrix. No.
Oh, 0.
0. Sum of the diagonal, right? Minus 1 plus 0. So the trace of A is 0. Calculating the trace is really the easiest thing, right? What is the trace of B? And don't let all the details get you off focus, right? It's just summing the diagonal elements. It's 0 minus 1/2 plus 1/2. So it's again 0. Do you agree? So that was that was property number 2. Anyway, good? What is the rank of A? What is the rank of A? Right. A is already in echelon form, right? It has a row of zeros, so the rank is 2. So the rank of A is 2. And by the way, from this we know automatically what is the determinant of A. 0. Why?
But there is a row of 0.
Okay, that's one way to say it. I wanted to say it from this. The rank of A is not full. It's not n. N is 3 in this case. Therefore, A is not invertible. Okay, and therefore its determinant is 0. Okay, so let's calculate the, we have now 2 options. Either we calculate the rank of B, and we'll find out that it's 2, and it will follow automatically that the determinant of B is 0, because B is not invertible, right? Or we can calculate the rank of sorry, the determinant of B, it's going to be 0, and it's going to follow that the rank, that,
It's not full, but we don't know.
it's not full, but we don't know that, right. So it's better to calculate the rank of B. Once we know it's not 3, the determinant is going to be 0. Okay, so let's do that. So let's take
Connect to row 2 and 3. Row 2 and 3 is
right. So okay, I'm just thinking, do I want to really write this? But yeah, let's do it quickly. 0, negative 1/2, 1/2, negative 1. Please allow me to do this. B goes to, this is the first row operation. Okay, good? Everybody understand what I'm doing? This is B, and the first row operation that I'm going to do is just add row 2 and row 3. Okay, good? So B, by adding row 2 and row 3, this becomes a 0, this becomes a 0, and this becomes a 0. So it's pretty trivial. So I have negative 1, negative 1/2, negative 1/2, and here's my row of zeros, right? So already I know that the determinant of B is also 0, because it's not invertible, because its rank is not full. Good? But this still doesn't mean that the rank is 2, but it does, because these two rows are linearly independent. So in fact, I even know, without going all the way to the echelon form, right, I already know that this is equal to the rank of B. Okay, so I'm assuming that you, in fact, already feel comfortable with these ideas, and so I'm not doing all the details, but I think you can follow, right? Good? So nothing difficult in this example, but you can see that indeed two matrices that represent the same map, therefore are similar, share these three properties. Good? Okay, so we're going to stop this one here. We're going to see later that there are more properties shared by similar maps, but we need to define them first. So we'll do that later.